This is William Michael of the Classical Liberal Arts Academy, and this is the first hour of freshman mathematics. This lesson is intended for high school freshmen to provide them with 1 hour of high school study in mathematics. In this first lesson, we're going to work through the definitions that are required for us to study algebra. You can find these definitions in the opening lesson of Ray's Primary Elements of Algebra, which is provided for free in the Classical Liberal Arts Academy. We're simply going to walk through the study of these definitions in this first lesson and fulfill our first hour of freshman mathematics. Let's begin. In algebra, quantities are represented by letters of the alphabet. Quantities are represented by letters of the alphabet. In other words, letters are used as symbols to represent quantities. So in order to understand what we study in algebra, you're going to need to understand what quantities are, and then understand that they are represented or symbolized by letters in algebra. In the second definition, we find the definition of quantity. Quantity is anything that is capable of increase or decrease. Quantity is anything that is capable of increase or decrease. So we learned that in algebra, quantities are represented by letters of the alphabet. And here, in this second rule, we learn that quantity is anything that is capable of increase or decrease. Now you may wonder, what does that mean? What does it mean, anything that is capable of increase or decrease? Well, think about it. There are many things that we can talk about that are not capable of increase or decrease. For example, if I were to name a man like St. Paul, St. Paul is an idea in our minds that we speak about, and it cannot increase or decrease. It's an individual man that we speak about, and as a man, there's no increase or decrease. There's just one man. Or I can talk about man as a class or a category of things. A man is a rational animal, but a man cannot increase or decrease. He can't be more man or less man. A creature is either man or he's not man, because man is a substance. The same would be true of a stone or a mountain. The stone, to be a stone, cannot be more or less stone. It's either stone or it's not stone. The same is true of a tree. To be a tree, a plant is either a tree or not a tree. It can't be more tree or less tree. We don't look at one tree and say, that's not as much of a tree as that tree. They're both trees equally because they're substances. But if we were to talk about a quantity, we might say this rock weighs more than that rock. The weight of the rock or the weight of the stone is a quantity. It can increase and diminish. We can increase the weight of something. We can decrease the weight of something, or sometimes by growing, the weight or size of something can increase or decrease. Anything capable of increase or decrease is a quantity. And so we see that things themselves are not quantities, but a quantity is an idea, a concept that is capable of increasing or decreasing. And in rule number 2 here, we see that quantity is anything that is capable of increase or decrease, and we're given some examples. For example, numbers. The idea of a number. Numbers can increase and decrease by addition and subtraction, by multiplication and division. Lines in geometry. A line is a quantity. We can increase a line in length, or we can decrease a line in length. Space, the area that a body occupies, or empty space. The space may increase or decrease. Time is another example of a quantity. Time may increase or decrease. So why would we want to symbolize quantities with letters? Why would we want to symbolize quantities with letters? The reason is because quantities can change. Quantities can increase and decrease. And because quantities can change, sometimes we need to think about quantities and leave room for them to change. We can identify relationships between different things, between different quantities, and we can express those relationships in a way that allows for the quantities to change. And we'll learn more about this later. So the reason why we want to represent quantities with letters is because quantities can change. They can increase or decrease. Let's go on to the next point in our lesson. We learn about 2 kinds of quantities. So we know what a quantity is, anything that is capable of increase or decrease. Now we'd like to know, what are the 2 different kinds of quantities? What are the 2 different kinds of quantities? In rule number 3 and 4, we learn the 2 different kinds of quantities. First, quantity is called a magnitude when considered in an undivided form. Quantity is called a magnitude when considered in an undivided form, as a quantity of water, given as an example. It's easy to understand what a magnitude is because a magnitude is one thing. It's one thing, an undivided form. A magnitude is one thing. It is a body that is an undivided form. It's one thing. And when we talk about a magnitude, we don't talk about the number, but we talk about the size of a magnitude. Magnitudes are measured in size. Even if you look at the word magnitude, magna comes from the Latin magnus, which means great, great in size. So a quantity is called a magnitude when considered as an undivided form, or in an undivided form, a single thing. We talk about the magnitude. It is capable of increasing or decreasing in size. And that's why the example given is a quantity of water. We don't talk about water with number. We don't say 1 water plus 2 water equals 3 waters. When we talk about water, we're talking about a body of water, and we measure water in size. We might say gallons or cubic feet of water, cubic meters of water. We measure water based on its size because water is a magnitude, a quantity of water, that is, not water itself. Water itself is a substance. So water cannot be more or less water than other water. Water itself is a substance. Water itself is not a quantity. But when we talk about a certain amount of water, that amount is a quantity because it can increase or decrease. The second kind of quantity is called multitude. Multitude. So first we have magnitude, and now we learn the second kind of quantity is multitude. Our rule states, quantity is called multitude when made up of individual and distinct parts. Quantity is called multitude when the quantity is made up of individual and distinct parts, such as 3 cents. 3 cents. In a multitude, we have a number of things, and these things are the same. A number of the same things makes up a multitude. So if we talk about 3 cents, the unit is 1 cent, and we ask, how many of these individual things, if we think of a cent, for example, as a penny, how many pennies are in this quantity? If we can count a number of different things, of individual and distinct parts in a quantity, then that quantity is a multitude. 3 cents is an example of a multitude because the quantity contains 3 parts, 3 individual and distinct parts. 3 cents. So the two kinds of quantity are magnitude, which refers to one thing that's measured in size, and multitude, which refers to a number of things that are measured in number. How many? Magnitude asks how much. Multitude asks how many. These are the two kinds of multitude. Now, this can get a little bit confusing because if I were to say 3 gallons of water, 3 gallons, and if I were to ask you, is this a magnitude or a multitude? It would depend on whether the water was divided into individual and distinct parts, or whether the water existed in one undivided form. So, for example, if there was a tank of water, and inside that tank there was 3 gallons of water, all together as one body of water, that would be a magnitude measured in size. But if I were to divide that water into 3 containers, 3 1-gallon containers, and then say, this is a multitude, there are 3 1-gallon containers, there are 3 gallons of water, then I would be referring to the quantity as a multitude. So that can be a little confusing. It depends whether the quantity is one undivided form, measured in size, or in individual and distinct parts, measured in number. But the two kinds of quantity are magnitude and multitude. So now let's back up a little bit and understand how this helps us. In the very first point, we learned that algebra, which is the subject of this first course in mathematics in high school mathematics, we learned that in algebra, quantities are represented by letters of the alphabet. We then ask the question, well, what are quantities? We can't use a word in a description or a definition if we don't know the meaning of that word. In algebra, quantities are represented by letters of the alphabet. What is a quantity? And then in rule number 2, we learned that a quantity is anything that is capable of increase or decrease. And we learned a few examples: numbers, lines, space, time, etc. Quantity is anything that can be increased or diminished. So in algebra, we use letters to represent things that are capable of increase and decrease. We use letters, because the letters do not change, to represent things that can change. That's really what we're doing in algebra. We're moving on from simple arithmetic to more complex real-life mathematics. In real life, we have to solve problems, and in those problems, things change. And yet we still need rules. But how can we make rules when things are changing? Algebra is a mathematical science that helps us to represent things that can change using symbols that do not change. And we'll see why this is important later in our studies. We're not studying algebra for its own sake. We're studying algebra because it will help us to use mathematics to solve complicated problems. So in algebra, quantities are represented by letters of the alphabet. Letters of the alphabet which do not change are used to represent quantities that are capable of increase or decrease. And then we learn that there are two different kinds of quantities. Magnitude, which is a quantity that is in an undivided form. It is one. It cannot be counted with numbers. It is one thing. And we measure a magnitude, in size. And then we learned the other kind of quantity is a multitude, which is made up of individual, distinct parts collected together in a group. And we measure these in number. And we saw one example would be 3 cents. And I explained how this can be a little confusing when we talk about something like 3 gallons of water. Is that a magnitude or a multitude? If all the water is together in one body, it's a magnitude. If that water is separated into 3 distinct parts, as in containers, then we have a multitude, and we would speak of a multitude. So that's an understanding of quantity and the two different kinds of quantity. Let's go on to rule number 5 here. One of the single parts of which a quantity of multitude, notice we're talking only about multitude here in number 5, one of the single parts of which a quantity of multitude is composed is called a unit of measure. A unit of measure. One of the single parts of which a quantity of multitude is composed is called the unit of measure. This is the thing that we count. This is the individual part that's counted in a multitude, the unit of measure. Thus, 1 cent is the unit of measure of the quantity 3 cents. So if we have the quantity 3 cents, which is a multitude, and we were to ask, what are we actually counting in this quantity? What are we actually counting? We're counting how many times 1 cent is contained in the quantity 3 cents. what we're counting is called the unit of measure. And unit just means one thing. So when we look at a multitude and we ask, how many? The first thing that we have to establish is, what are we actually counting? What is the one thing that we're counting in this quantity? What is the one thing? What is the unit of measure? The unit by which we're going to measure the multitude. The unit of measure. Rule number 5 goes on to say that the value or measure of any quantity is the number of times it contains its unit of measure. The value or measure of any quantity is the number of times it contains its unit of measure. So when we look at a quantity and we want to measure that quantity, the first thing we need to determine is whether or not we're going to measure a magnitude, one thing, or whether we're going to measure a multitude. If we're going to measure a multitude, we need to ask, what is the unit of measure? What is the one thing that we're going to count to number how many times it's contained in this quantity? We have to know the unit of measure, and then we have to add how many times that unit is contained in the quantity. And that number that tells us how many times the quantity is contained in, how many times the unit, is contained in the quantity. How many times the unit is contained in the quantity, that number is called the value of the quantity, or the measure of the quantity. The value or measure of any quantity is the number of times it contains the unit of measure. So in number 5 here, we're talking about multitudes. Make sure that's clear. Rule number 5 is referring to how we measure multitudes. We identify the unit of measure, and then we count how many times that unit of measure is contained in the multitude. The value or measure of any quantity is the number of times it contains its unit of measure. Now let's go on to point number 6. And notice in point number 6, we begin talking about magnitude. So rule number 5 was focused on finding the measure of a multitude. In a multitude, we count how many times the unit of measure is contained in that quantity. And the unit is an individual and distinct part that we can number in the multitude. But now in Rule 6, we ask the question, how can we measure magnitudes? If a magnitude is one undivided form, it's not made up of different parts. It's not made up of individual and distinct parts like a multitude. A magnitude is one undivided form. How then can we measure one thing? How can we measure a magnitude? This is the subject of point number 6 here. In quantities of magnitude, there is no natural unit. There is no unit in a magnitude. It is one undivided form. So there is no natural unit for us to use to measure the magnitude. There is no natural unit. So what we need to do is we need to make one up. We need to determine what we would like to use to measure the magnitude. Rule 6 tells us there is no natural unit. So it is necessary to fix upon or choose an artificial unit. That is a unit that we make up, that we choose to use. It is necessary to fix upon an artificial unit as a standard of measure. And then, to find the value of the quantity, that is, of the magnitude, we ascertain or count how many times that magnitude contains the unit of measure that we have chosen. So when we're looking at a multitude, because it's a multitude, we can see the unit of measure. That's what makes it a multitude. We can see that there are a number of things collected together in a group. For example, 3 cents. If we have 3 pennies, we can look at that quantity and see that it contains a number of individual and distinct parts. We may not know how many there are. 3 is a simple number, but imagine if there was a pile of pennies sitting on a table. We could see that it was a pile, a quantity, a multitude made up of pennies, but we wouldn't be able to easily tell how many there were. We would simply see that it's a multitude and that it's made up of a number of individual and distinct parts. If we wanted to count or measure that quantity, that multitude, we would simply begin counting the individual objects, the natural units that make up that multitude. But if we have a magnitude, there is no natural unit. It's not made up of a collection of individual and distinct parts. It's one undivided form. And so for us to measure the magnitude, we have to ascertain an artificial unit of measure. We have to choose something to use, some quantity to use as a measure, and then find how many times this quantity contains the measure that we've chosen. So, for example, if we had a tank full of water and someone asked us how much water is in the tank, there would be no way for us to answer that question. We would first need to establish a unit of measure. So I would need to tell the person, if you'd like to measure how much water is in this tank, you need to choose a unit of measure. And the person could walk over to the counter and grab a spoon and say, let's measure it in spoonfuls. And we could begin counting. We could take the water from one tank and move it to another tank, one spoonful at a time, and measure the quantity by how many spoonfuls it contained. Notice what we're doing here is we're dividing the magnitude into a multitude of units. We're actually creating the multitude by dividing the magnitude, but we choose the unit of measure. He could also hand me a cup and say, let's measure how many cups are contained in that tank. And we could count and say, it contains 65 cups. We could also use a gallon. He could hand me a gallon container and say, let's measure how many gallons of water are in that tank. So you see that the quantity, the unit of measure, is artificial. We can pick anything we'd like. We could use our hands, and we could ask how many handfuls of water are in that tank. So to measure a magnitude, we have to create the unit of measure, and then we count how many times that unit of measure is contained in that quantity. But in a multitude, in measuring a multitude, there is a natural unit of measure. That is the one thing that the multitude is made up of a number of times. So in quantities of magnitude, there is no natural unit, and it is necessary to fix upon an artificial unit as a standard of measure. And you should know the difference now between a natural unit of measure and an artificial unit of measure. A multitude has a natural unit of measure. A magnitude needs an artificial unit of measure. And you should know why. Why does a magnitude need an artificial unit of measure? It is necessary to fix upon an artificial unit as a standard of measure, and then to find the value of the quantity, we ascertain or count how many times it contains the unit of measure. Thus, our textbook goes on to say, to measure a length of line. If we have a length of line, and just for the sake of illustration, let's imagine a string. If we have a certain length of string, how can we measure the length of the string? It's one undivided form. A length of string is a magnitude. It's one undivided form. How can we measure the length of a line or of a string? The first step is to take a certain assumed distance, to fix upon an artificial unit of measure. Now, like I said, we can use whatever we want to measure a distance or to measure a magnitude. For example, on a farm, if I'm planning out a garden or a fence, and I'd like to get a good idea of how far it is from, let's say, the corner of the barn to the back corner of the garden area, I might simply walk from the barn to the back corner of the garden and count how many of my own feet are contained in that distance. And that's good enough for me to have a measure of that distance, which is a magnitude. But if we're going to communicate with other people, if businesses are going to communicate with other businesses, if cities are going to communicate with other cities, we can't use whatever units of measure we like. For example, if I said the distance from the barn to the back corner of the garden is 300 of my feet, how could another person measure that if his feet are different size? The unit of measure would be different, and that would make the value different. So what we normally do is we use common measures or common units of measure. In our book here, we read this: to measure the length of a line, take a certain assumed distance called a foot. So a foot is an example of a common unit of measure that all men can use to measure magnitudes. So take a common distance, a certain assumed distance, a foot, and then use the foot to measure how many times that line contains that quantity, the foot. So if we measure and we find that the line contains the foot 5 times, we say that the line is 5 feet long. 1 foot would be the unit of measure, and the value of the line would not be the number 5, but 5 feet. The line, the quantity that we're talking about, the quantity contains 1 foot 5 times. It's 5 feet in length. So this is how we measure a magnitude. Let's go on to number 7. The numerical value of a quantity is the number that shows how many times it contains a unit of measure. The numerical value of a quantity is the number that shows how many times it contains a unit of measure. Thus, the numerical value of a line 5 feet long is 5, just the number. The numerical value refers to just the number of units, not the unit also, just the number, how many. The numerical value is the number that shows how many times a quantity contains its unit of measure. Thus, the numerical value of a line 5 feet long is simply 5. The same quantity may have different numerical values. The same quantity may have different numerical values if the unit of measure changes. The same quantity may have different numerical values according to the unit of measure measured. So if the line was 5 feet long, the unit of measure would have been 1 foot. And the numerical value of that quantity would be 5. But if we decided to use 1 inch as the unit of measure, that line would contain 60 inches. So the same quantity would contain 5 feet, and it would also contain 60 inches. The numerical value in the first case would be 5. The numerical value in the second case would be 60. So if the unit of measure changes, the numerical value of the quantity changes. This happens in magnitudes, but not in multitudes, because multitudes have a natural unit. What this teaches us is that we have to be careful that any time we talk about any quantity, any time we think about any quantity, we cannot think of it as a numerical value alone. We always have to make sure we're aware of what the unit of measure is that's being referred to by a numerical value. So when we compare different quantities, we always have to make sure that we're using the same units of measure to measure the quantities. That may seem obvious. Who would ever measure 2 different quantities with 2 different units of measure? Well, no one would do it intentionally. But sometimes it can happen accidentally, especially when we're sharing information. For example, if I measure a field, let's say a football field in America, in yards, and I ask someone living in England, how long is a football field? And for someone living in England, they don't measure in yards, they measure in meters. And so they may respond and say to me that a football field is so many meters long. And if I'm not paying attention to the unit of measure, I'll hear two different numerical values. So I need to make sure that I'm always careful with units of measure, because numerical value doesn't tell us the whole story about a quantity. We also have to know what the unit of measure is that was used and counted to find that numerical value. This is especially a problem when we have different systems of measurement. Like I said, if in America we use inches and feet and yards and miles to measure length or distance, and in another country they use centimeters and meters and kilometers to measure distance, we can get very confused if we're not careful to convert one unit of measure or one quantity into its equal using that other unit of measure. So we need to see that numerical value can change in a quantity if the units are not the same. And anytime we try to solve any problems, we're going to always need to make sure that we know what unit of measure was used to measure a quantity, and that we keep the units of measure always the same. So that covers number 7 there on the numerical value of a quantity. In number 8, we finally define what a unit is. And I've already told you this definition, but number 8 tells us that a unit is a single thing of an order or kind, a single thing of any kind. A unit is a single thing of any kind. Anything that you can refer to as one, anything that you can refer to as one is a unit. So if I say, do you have a pencil? And you can look and you can see if there is one pencil. Anything that you can refer to as one is a unit. If I can say, let's measure this in inches, the one thing that we're going to use to measure is a unit. That's what we're calling one. Anything that we refer to as one is a unit. Next, number 9. A number is an expression denoting a unit or a collection of units. So a number is simply a collection of units. It's important for you to understand here in this first lesson in algebra exactly what a number is. Many people use these words, but never actually define them. What is a number? A number is one or more units, a collection of units, but it may also be one unit. A number is an expression denoting a unit or a collection of units. In number 10, we go on to talk about two different kinds of number. Two different kinds of number. Before, we talked about quantity and the two different kinds of quantity. We talked about magnitude and multitude, two different kinds of quantity. Now we've learned about number. We've learned what number is, and now we're going to talk about two different kinds of number. So don't get the two different kinds of number confused with the two different kinds of quantity. Two different kinds of number. A number is an expression denoting a unit or collection of units. And the two different kinds of number are abstract and concrete. Abstract and concrete. The two different kinds of number are abstract and concrete. First, we learn that an abstract number denotes how many times a unit is to be taken. An abstract number denotes how many times a unit is to be taken. A concrete number denotes the units that are taken. A concrete number denotes the units that are taken. So to go back to number 7, when we give the numerical value of a quantity, the numerical value is expressed with an abstract number. An abstract number is a number that does not include or identify any unit of measure. An abstract number is a number without any reference to a unit of measure. The word abstract means drawn away from. An abstract number is the idea of a number drawn away from the actual things that are being numbered. It's the number itself. The number abstracted from or drawn away from actual material things that are numbered, the units themselves. And concrete number is the number included with the unit. A concrete number is the number with reference to things, but an abstract number is a number with no reference to any things. Abstract number denotes how many times a unit is to be taken. A concrete number denotes the units that are taken. The rule goes on to say, thus, 4, the number 4 by itself with no reference to units, 4 is an abstract number, denoting merely the number of units taken. 4 feet, on the other hand, 4 feet is a concrete number because it denotes what unit is taken as well as the number taken. So if an expression includes the units, it is a concrete number. If a number does not include the unit, it is an abstract number. The rule goes on to say a concrete number is the product, speaking of multiplication, a concrete number is the product of the unit of measure by the corresponding abstract number. A concrete number is the product of the unit of measure multiplied by the corresponding abstract number. Now, these things may seem just like boring math facts, but we're going to understand that the author of this book is helping us to think clearly about numbers and quantities. Because if we learn to think about them in this right way, it will help us to understand algebra. So this is not just meaningless mathematical information. This is actually helping us to think carefully about numbers and quantities, because this is going to make sense out of algebra when we begin to learn the rules of algebra. Notice that the author is helping us to understand different kinds of number. One number that doesn't include any reference to a unit of measure, and another kind of number that includes a reference to a unit of measure. So when we say something like 4 feet, we have to think of exactly what we're saying. We have to think of it clearly. We're talking about a number of a certain unit. And the author tells us that it's helpful for us to realize that there is a multiplication going on here. Anytime we think of a concrete number, we think of both an abstract number and a unit of measure being multiplied together. A concrete number is a product of an abstract number multiplied by some unit. A concrete number is actually a product of an abstract number being multiplied by some unit. It's important for us to understand that idea of a concrete number. Thus, the rule goes on to say, $6 equals $1, that's the unit of measure, multiplied by 6. $6 is a concrete number. It expresses a product of $1, that is the unit of measure, multiplied by the abstract number 6. It can also mean $1 taken 6 times. So anytime we hear a concrete number or read a concrete number, we're to remember this important lesson because this is going to help us understand algebra. A concrete number, $6, 4 feet, 3 cents, 50 miles, 100 pounds. Any concrete number that we hear or read is the product of some abstract number multiplied by a unit of measure. Remember that I told you that this is going to be very important in our study and understanding of algebra. So in your notes, in your studies, draw a star next to this definition of a concrete number, because we're going to come back to this in future lessons, and if you don't study this carefully, if you don't understand this idea of a concrete number, you're going to struggle to understand algebra. And if you write to me and say, Mr. Michael, I'm confused, I can't understand how algebra works, I really just can't get it, I'm going to say, go back to the first lesson in algebra. Go back to rule number 10 and read what the author taught us about concrete number. Because this idea of concrete number is where algebra finds its beginning, as we'll see. Let's wrap up this lesson with rule number 11 here. We read, in algebraic computations, or in the computations that we're going to carry out in algebra, unlike the computations we carried out in arithmetic. In algebraic computations, letters are considered the representatives of numbers. Letters are considered the representatives of numbers. And we're going to stop there as far as content goes for this first lesson in algebra. So we've covered rules or articles 1 through 11 in this first hour of freshman mathematics studying algebra. We've learned about what algebra is in a general kind of description. Back in article number 1, we read that in algebra, quantities are represented by letters of the alphabet. And in reading that description, you should ask the question, what exactly are quantities? Everyone thinks that they know what a quantity is, but what really is a quantity? You should be able to give an exact definition because this is a real study of quantity. So what is a quantity? In article number 2, we learned a quantity is anything that is capable of increase or decrease. And I gave you examples to show you that not everything is capable of increase or decrease. One man isn't more or less man than another. Socrates cannot be more or less Socrates. A rock can be not more or less a rock than another rock. A tree cannot be more or less of a tree than another tree. Those things aren't quantities. But quantities can be things like numbers, lines, space, time, things that can increase and decrease. That's what a quantity is. We then learned about the two kinds of quantity. We learned about magnitude and multitude. You should be able to explain the difference between magnitudes and multitudes. Remember, I also explained how these can be confusing. Make sure you remember why they can be confusing and understand how to sort that out so that you're not actually confused. We then learned about how to measure different quantities. We learned about how to measure a multitude and how to measure a magnitude. Make sure you understand the difference between how we measure a multitude and how we measure a magnitude. We learned about units of measure and numerical value. Then in article number 8, we learned clearly what a unit is, and in article 9, what a number is. And then in article 10, we learned the two different kinds of number, abstract number and concrete number. We learned that a concrete number, it's important to understand that a concrete number is the product of a unit of measure multiplied by an abstract number. And note that in the textbook, the author put that line in italics because it's important. And then lastly, we finished with Article 11, which says, in algebraic computations, letters are considered as representatives of numbers, and they can be abstract or concrete numbers. So that's all for the content of this first lesson in freshman mathematics. We've covered articles 1 through 11 in Ray's first book of algebra. This fulfills your requirement for 1 hour of instruction in freshman mathematics. In order to prove that you've completed this hour, you need to complete the quiz that's included in the lesson, a simple quiz about the content of this first hour. I hope that that was helpful. If you have any questions about anything that I discussed or would like to go into any of this in further detail, I encourage you to do that by actually studying the Algebra 1 course in the Classical Liberal Arts Academy. You can do that in addition to this freshman math course, and that's what I'd recommend you do. So I hope that that's helpful. I'm going to wrap up now for this first hour in freshman mathematics. Again, this is Mr. William Michael of the Classical Liberal Arts Academy. God bless your studies.